Welcome to a review of pre calculus material. In this course, we are going to try and accomplish two objectives. First, we will review some material from high school, exploring some well-known techniques, allowing you to fundamentalize some of those techniques. These techniques include factoring, completing the square, etc. We will review a specific way to do this. Now, for these techniques, like solving trig functions, there are many ways in which you can do this. The technique we will cover works. There are other techniques that also work. So if you prefer another technique, that is pretty okay. Additionally, we are going to introduce some new material that will be used heavily within your first year calculus courses. Without further ado, let's get started. We are going to start with sets and set notation. Now, sets are a new topic. A set is a collection of distinct objects grouped together. The objects are called elements. We use open curly bracket and close curly bracket to bound the elements when forming a set. For example, S equals the set containing A, B, 1, 2. We say that S is a set that contains 4 elements. And the elements are A, B, 1, 2. To indicate that an element is inside a set, we use the notation within. To indicate that an element is not within a set, we use the notation not within. For example, 1 is in our set S, and 3 is not in our set S. Now, with sets, we can have intersections and unions. The intersection of two sets S and T is denoted by S intersect T. The intersection is the collection of all elements in both S and T. The union, however, of two sets, S and T, denoted by S union T, is denoted by S union T. The union is the collection of all elements in either S or T. Now, to understand this, I find it's typically easiest to think about a Venn diagram, or two circles coming together. S union T is anything that is in either set, whereas S intersect T is in the intersection of both sets. So let's practice. We've got the sets A, B, 1, 2 being our set S, and set T being 1, 2, 3, 4. Now, when we take the intersection, we're asking what is in both. So the set containing the elements in both is the set containing 1, 2, because those are the elements that are in both. Whereas and that's our intersection. The union is the set of elements that is contained in either set. So A is in S1, B is in S1, 1 is in both, 2 is in both, 3 and 4 are in T. Now notice that we do not write 1 or 2 twice. We have one representation for every element within our set. We don't repeat it. Now, we talked about the intersection of these sets. We can also talk about a collection within the set. And if we take a collection within the set, we call this a subset. We say that S is a subset of T, denoted S subset T, if every element in S also appears in T. We denote S not being a subset of T with S is not a subset of T. Now, if S is a subset of T, but T is not a subset of S, then S is a proper subset of T. And this allows us to define a proper subset. But if S is a subset of T and T is a subset of S, then S equals T. This is how we define the equality of sets. Two sets are equal if both sets are a subset of the other set. Now, we have learned a lot of definitions here. We've learned subsets, proper subsets, sets equality, intersection, and union. Let's compare these sets to see how they're related to each other. So let's compare T and S. T and S share the same elements. So T is a subset of S, and S is a subset of T. Therefore, S equals T. Now, if we compare T and R, T is not a subset of R, and R is not a subset of T. Likewise, S is not a subset of R, and R is not a subset of S. Now, what about R and Q, or TS and Q? Well, Q is a subset of T, Q is a subset of S, and Q is a subset of R. T is not a subset of Q. S is not a subset of Q, and R is not a subset of Q. What's interesting here is that Q is a subset of all three of these sets, but R is not a subset of S, and S is not a subset of R. So as a practice with these sets, I highly encourage you to take the union and intersection of the sets T, S, R, and Q. We now move on to our number systems. Now, there are many different number systems, and as you explore more algebraic structures within your algebra classes that you may eventually take, you'll learn more and more about these number systems. For pre-calculus, we care about 5 number systems, or mainly we care about 5 number systems. They are the natural numbers, which is the set 1, 2, 3, so on and so forth. Note that these are sometimes denoted 0, 1, 2, so on and so forth. We have the integers, which is the set -3, -2, -1, 0, 1, 2, 3, so on and so forth. We have the rational numbers, which is the set R equals P over Q, such that P and Q are integers and Q does not equal 0. Now, this notation is something you're probably used to, but we can also define it differently. We can define it as R equals P over Q, where P is an element of the integers and Q is an element of the natural numbers, where P and Q are co-prime. Now, this definition here, we don't need to worry too much about, but I wanted to highlight this for 2 reasons. One, we can define sets in different ways. Different definitions can be used to explain the same set. And 2, sometimes our definition is useful practically, while other times we define it specifically to be useful theoretically. And the different definitions have different benefits. Because we're more interested in using rational numbers than the theory of rational numbers, we are mainly going to use this definition. You can think of it as an integer divided by another integer, and that is just fine. Then we have our real numbers. And the real numbers are numbers that can be written using a finite or infinite decimal expression. And you think we're used to thinking this as all our numbers. But there's actually another number system we're going to talk about called the complex numbers. And what the complex numbers do is they allow us to solve expressions, particularly this expression. And we can actually get a solution for it. And it expands the numbers we can look at and expands the expressions that we can solve. Now, we talked about our rational numbers, and we talked about how there were multiple representations, but we also have our irrational numbers. All rational numbers are real numbers that either have a finite decimal expansion or a repeating decimal expansion. So there's either a pattern that shows up or it's finite. Now, any real number that does not have a repeating pattern is called irrational. This includes some very important numbers. It includes pi, square root of 2, and e. Now, pi and e are very important in calculus. We will be using these two irrational numbers very often. Now, these numbers, they create something called a total ordering. And what a total ordering means is that we have a subset, which is a subset of another set, which is a subset of another set, which is a subset of another set, which is a subset of our final set. Every set is a subset of the next set. There's a way to order them using subset. Now, we do not need to know what this means, but when you go into higher mathematics, you'll learn more about partial orderings and total orderings in future courses. And before we move on to more review, I wanted to make a quick remark about the definition of rational numbers. If we think about the numbers minus 3 over 4, minus 3 over 4, and 3 over minus 4, they're all equal. And note that minus 3 over 4 is technically minus 1 times 3 over 4. That means that this expression here is not a rational number technically. It's minus 1 times a rational. But when we compute solutions, these are all the same. And if you were to give an answer, all of them would be okay. But if we look at our rational numbers, the way that we defined it, where it's one integer over another, we have two different possible representations. This means that the representation is not unique. When using the second definition, however, only minus 3 over 4 would be considered a rational number. Under this definition, every non-zero rational number has a unique prime representation. And this is really important theoretically, but not practically. We're not going to explore this too much here, but we can already see that if we define sets a specific way, they have additional properties or don't have those properties. So the practical definition didn't give us uniqueness, but the theoretical definition did. And in future courses, you may be really interested in defining it such that you get this uniqueness property.